Global temperatures are escalating, and with them, an exponential demand for space cooling. By the end of this century, projections indicate over 8 billion people will face heat and humidity levels that push past the biological thresholds of human survivability. Traditional compression-based air conditioning presents a paradox. These systems rely on fossil fuel-generated electricity and high GWP refrigerants, meaning the more we cool our buildings, the more we accelerate planetary heating. Mechanical cooling also fails to eliminate thermal energy. It simply displaces it from the inside of a building to the immediate outdoor environment. This waste heat intensifies the urban heat island effect, driving localized temperatures even higher. To break this cycle, material scientists have developed a zero-energy thermodynamic alternative known as passive daytime radiative cooling, or PDRC. PDRC exploits an optical anomaly. While greenhouse gases block most outgoing infrared radiation, a natural transparency window exists between 8 and 13 micrometers. It bypasses the greenhouse gas blanket by establishing a direct thermodynamic conduit, allowing a surface to dump heat straight into the infinite 3 Kelvin sink of deep space. Achieving sub-ambient temperatures in direct sunlight requires a material to cross a mathematical threshold known as net cooling power. This energy balance equation calculates net cooling. The primary driver is P-rad, the thermal power actively emitted to the vacuum of space. P-sun must be subtracted. The surface must reflect nearly all solar radiation, or solar heat instantly overwhelms the cooling. P-at is also subtracted, but because air is transparent in the 8 to 13 micrometer window, very little downward thermal radiation returns. Finally, non-radiative gains from conductive and convective heat transfers are deducted. Engineering a PDRC material is a delicate balancing act, where the outgoing radiation must outpace the combined solar, atmospheric, and convective heat gains. Radiative cooling is strictly bound by local atmospheric moisture, measured as the precipitable water value, or PWV. Because water vapor is highly emissive in the infrared, a high PWV closes the atmospheric window, trapping heat and stifling the surface's net cooling power. This creates two categories: selective emitters with a narrow peak and broadband emitters with a wider plateau. Selective emitters focus exclusively on the 8 to 13 micrometer window for deeper cooling, but fail if condensation ruins their tuning. Broadband emitters absorb more atmospheric back radiation, but their sheer power makes them highly effective at rejecting above-ambient heat across a wider spectrum. In hyper-arid environments with low humidity, the atmosphere is transparent across much wider bands. In these dry regions, cheaper, unselective broadband emitters actually deliver higher net cooling power than precisely tuned metamaterials. Stanford experimentally validated daytime sub-ambient cooling in 2014 using a 7-layer photonic crystal on a silver substrate. It achieved high spectral selectivity, but the precise vacuum deposition process remains too slow and expensive for building-scale deployment. To reach the scale needed for urban heat mitigation, researchers at Purdue University developed a barium sulfate acrylic nanocomposite. Barium sulfate's high electron band gap minimizes solar absorption, and its natural phonon resonance enables high sky window emissivity. By utilizing a broad distribution of particle sizes, the paint leverages Mie-scattering to reflect 98.1% of incoming sunlight. By hacking geometry and chemistry simultaneously, researchers turned a delicate nanophotonic experiment into a drop-in, scalable industrial coating. Static broadband coolers have a critical flaw in seasonal climates: the winter heating penalty. Because a static cooler rejects heat year-round, it forces building HVAC systems in mid-latitude cities to consume excess energy for space heating during the winter months. The solution is temperature-adaptive emissivity, specifically utilizing phase-change materials like vanadium dioxide. Vanadium dioxide acts as an autonomous thermal diode. When ambient temperatures reach 68 degrees Celsius, the molecular lattice snaps from a monoclinic state to a rutile state. Above the threshold, it shifts to a metallic state, instantly turning on high emissivity to vent summer heat to space. Below this temperature, it remains insulating, trapping heat inside the building envelope to prevent overcooling. In regions with clear seasonal skies, these dynamic phase change materials allow PDRC to reduce annual energy consumption without the risk of an unintended winter heating penalty. Field deployment introduces environmental threats that aren't present in a lab, beginning with the accumulation of atmospheric dust. Dust absorbs solar radiation. Accumulating as little as 1 gram of dirt per square meter can absorb enough heat to entirely negate the sub-ambient cooling effect. Engineers combat this with super-hydrophobic, self-cleaning surfaces utilizing the lotus effect. Spherical water droplets roll across the material, mechanically removing dust particles. However, relentless ultraviolet radiation eventually causes the oxidative decomposition of these polymers, ruining the self-cleaning effect over time. To ensure longevity, researchers use robust inorganic encapsulation, such as silicon dioxide films, to shield the active matrix from UV damage. Superior optical physics is only useful with environmental durability. Robust encapsulation is what provides the 5 to 10-year lifespan necessary for commercial viability. PDRC is now moving beyond basic roofs and into direct integration with commercial HVAC infrastructure. By utilizing PDRC panels to subcool the refrigerant exiting a standard condenser, operators can expand cooling capacity while drastically reducing the compressor's electrical load. The socioeconomic impact is even higher in developing economies. In India, an estimated 1.1 billion people are at risk of exposure to lethal heat conditions. Informal settlements often use corrugated metal roofs that act as thermal amplifiers, driving indoor environments to dangerous temperatures. Systemic PDRC deployment on these structures is projected to drop indoor temperatures by up to 5 degrees, potentially saving over 300,000 lives by 2030. In extreme climate zones, PDRC serves as critical resilience infrastructure, decoupling human survival from the high costs of mechanical air conditioning. The final scale of this technology is Earth radiation management, a form of planetary geoengineering. Unlike traditional solar geoengineering, which reflects incoming sunlight but disrupts global cloud dynamics, PDRC targets the thermal imbalance more directly. It works by explicitly enhancing the long-wave emission escaping through the atmosphere, cooling the surface without destroying stratocumulus clouds. Global PWV mapping shows that coating just 1 to 2% of the Earth's surface with PDRC materials could theoretically offset current anthropogenic net radiative forcing. The logistical reality depends entirely on humidity. PWV data reveals that equatorial tropics and maritime regions are virtually useless for deep space heat rejection. Deployment must target the hyper-arid, high-capacity landmasses of the Northern Hemisphere, where the air is dry enough to effectively vent planetary heat. PDRC has evolved from a laboratory anomaly into a scalable industrial tool. Whether cooling a single data center or theorized as a global thermal stabilization lever, it represents our most physically elegant mechanism for surviving a rapidly warming world.